not tell you. And it led to our ability to get the distances, the redshifts, not by taking spectra, but simply by taking images in different filters for the following reason. And it led to, I'm going the wrong way again, it led to the concept of what we call photometric redshifts, which I believe is one of the most important 2 or 3 results ever out of Hubble Space Telescope. I tell you that. The winner, of course, is the Nobel laureate research on the accelerating universe, okay? But if I had to pick number 2, I would say that photometric redshifts has opened the entire universe to interpretation. Because if you're going to interpret what you see out there cosmologically, you've got to get the distance. And to get the distance, you had to take a spectrum. And that takes a lot of telescope time. You're looking at one object, although now we are able to multiplex, but still. Rather than take an image where you can get 4,000 in the same amount of time. So here is how you do it. Here for the, let's see, this is the ultra. Here you see the filter bands in angstroms or nanometers that were used in the ultra deep field. Going from the atmospheric limit down near 3,200 angstroms out to 1 micron. Infrared's beyond that, okay? So this gray, these are the filters. Here is the spectrum of a galaxy that is nearby. No redshift, right? It's local. And here is what this spectrum would look like in these different filters if it's moved further out, expanding, and therefore the Doppler shift, we'll call it. The redshift takes that spectrum and transforms it into better wavelengths. What you will find is that for a galaxy that is local, and for this discussion, we'll assume that galaxies consist of billions of stars. They have temperatures 5, 10, 20,000 degrees. They radiate a Planck function, let's say, typically of 10,000 degrees. So you're basically seeing here a Planck function, although that's really oversimplified. You get absorption lines from hydrogen because at 10,000 degrees, your electron, some are up in the n = 2 level. The Balmer continuum gives you absorption at 365 nanometers. And so the Planck function, which already is steep because it's exponentially declining, is even steeper because the hydrogen is absorbing all that. So what you see is, for local galaxies, you'll actually get some flux down here in ultraviolet. But for an object that is further out and it's shifted here, you'll find no flux here. It's all been absorbed. So you'll get nothing here, but you will see it in these bands. And the further out it is, the higher the velocity because of the universal expansion, what you'll find is that you have what we call dropouts. That is, the galaxy at a great distance will not be visible in these 3 bands, but it will be visible here. So you have a clever way of getting the rough distance to a galaxy by simply taking images in 6 or 7 bands going out into the infrared and looking to see these dropouts. So here's an example of a series of images of 4 objects, starting in the visible band here at a half a micron, out to the H band in the infrared at 1.6. And so what you see are these dropouts. That is, so these are objects in the ultra deep field. And what you see here is nothing, and then boom, you see it suddenly appear in the infrared. So what do we know? We know that it must be at a distance, at a redshift, that causes its spectrum around 4,000 angstroms, where you get this drop from the Balmer continuum, to give you no flux here and flux there. So you can determine the distance to a galaxy simply, not by taking spectra, just the images. And what is amazing is that if you do this, and you actually get spectra for a subset of these things, you find a very good correlation between the actual spectroscopic redshift by getting the spectrum and comparing it with the photometric. And you can see that the dispersion here in redshift is really quite small. So it enables us to interpret all of these deep fields with tens of thousands of galaxies without having to get spectra. This is what I believe has been one of the truly transformational things of Hubble Space Telescope, because this is what has made all these cosmological studies possible. The deep fields validated the concept of photometric redshifts and has changed everything. And so with that, just a few minutes here before I'm thrown out. So, evolution of the universe. Okay, so Hubble has done all of these things. So let's try to piece it together, starting with either the COBE or more recently the WMAP satellite. You've all seen this, right? So we look back in the microwave background. You can see to redshift, and I can't remember what it is, 1,000 roughly to within 300,000 years of the Big Bang. And here are the temperature, therefore also the density and homogeneity is highly magnified. Tremendous homogeneity, differences of 1 part in 10 to the 5th, right? This is amazingly homogeneous universe. That, if you take that, expand it, what you find from the supercomputer calculations, here's one from the University of California. So this is the evolution of the universe in, I think this is 12 seconds. You start off with this inhomogeneity of 1 part in 10 to the 5th. The dense regions gravitationally contract, and so you start off homogeneous, you end up like this. Similar supercomputer calculation by my former colleague Piero Medal, same thing. Basically, you start off with homogeneous, you expand it, those inhomogeneities gravitationally collapse, and you end up, and you get merging of these clumps, and essentially, this is a computer simulation that we believe is realistic of how the universe evolved from the Big Bang and those initial 1 part in 10 to the 5th inhomogeneities to the current state. That is, it looks like that. So let me very quickly go through black holes. Okay. It turns out that in that picture, we expect the galaxies to build up from these initial small inhomogeneities through gravitational merging. And in fact, some of Hubble's neatest pictures are of galaxies that are interacting. If you do computer simulations, again, another supercomputer, here's 2 spiral galaxies gravitationally interacting. And here's what the computer shows. So we start off with some objects that look like this, gravitationally interacting, and there is dark matter in here. You'll see what happens. You get something that looks like the picture, the lower right-hand side that I showed you in the previous slide. Okay, maybe not such a great surprise. In any event, it is realistic to believe that the current galaxies did build up through mergers. And you start off with 2 morphologically similar objects that end up different. The morphology changes. But if I continue this, let's see, I think it's the next slide. Yeah, so if you continue this calculation now, let's see. Note what happens. So here are our merging systems. Get some phase mixing there, causing these rings, which are actually observed. And you get the 2 nuclei merging into a single nucleus. It is believed that the large mass concentrations that we observe in galaxies are formed this way. And they're sufficiently condensed that they form black holes. And the reason we think that is because with Hubble, when you actually measure the velocities of the nuclei of most galaxies, okay, here's a spectral line. So I'm putting the dispersion wavelength goes from blue to red. So this is probably the hydrogen alpha, the Balmer line. What you see is that you have very small velocity until you get near the center of the galaxy. Then it goes very blue, thousands of kilometers a second in a very short period of time, changes. So you can determine what mass is required to produce that and what the distance scale is. It turns out that the density is so great that it is greater than nuclear densities, and therefore we infer the existence of black holes. And it is believed that that is what quasars are. Essentially, it is material falling into supermassive black holes in the centers of galaxies that are heated up before it gets to the event horizon, and that is what we think quasars are. And I can show you here, for our own galaxy, now this is from a ground-based telescope. We peer into the center of our galaxy, and with a laser star optics, laser guide star optics, it turns out there are some stars, and we can actually plot over about 15 years the orbits of these stars around a very small section of the center of our own Milky Way, and we infer the existence of a 20 million solar mass object in a size that is roughly the size of the orbit of Pluto in our own solar system. Got to be a black hole. There's no force that we can, now we could be wrong, of course. We've just discovered a force that's causing the acceleration of the universe, but the Occam's razor conclusion is that you've got a very massive black hole here. So these are some of the really interesting science results that have come out of the Hubble. I didn't have anything time to say about the acceleration of the universe, but I'm sorry about that. And we believe that the James Webb Space Telescope, which will be sensitive to the infrared, will be really important because it will enable us to, I was going to say something about the frontier field. Let me just skip to the last slide, basically, and talk about this. What we're trying to do with this gravitational lensing, okay, the original deep field went out to within about 1 billion years of the Big Bang. With the better detector and the ultra deep field, we went out to about 500 million years. It is believed, again, if we have time flowing this way, you know, you got the Big Bang here, then because of the adiabatic expansion of the universe, before any stars or galaxies formed, there was what was called the dark ages. And then the cooling with those gravitational inhomogeneities caused the first galaxies and stars. With the Hubble, you can't quite see that far. But if we look at objects that are here that we can't detect them along the line of sight to a massive cluster of galaxies, we can use gravitational lensing to possibly pick up some of these things. And that's just what's come out in the past couple of days. Here is one of the massive clusters of this, what are called the frontier fields that I just mentioned, that Hubble is now doing and is going to spend almost 1,000 orbits on. Here is a dark matter lensing map of this rich cluster of galaxies. And what you can see is that there are some contours here that represent where you would expect to see distant galaxies fall if they were at a redshift, at different redshifts. And where are they? Here they are. The redshift 11, you would expect them, because the further away you are, the less diverging less diverging the sightline is for an extended object. And so the more distant objects would be a little further out from the cluster of galaxies. So for redshift 11, which is more distant than redshift of 3.5, which is more distant than redshift of 2, you would expect to see possible images of distant galaxies falling along these contours. And so what the frontier fields is doing is we have these groups of these consortia that are providing these maps, and then now large telescopes are taking spectra of objects here that follow along these contours to try to detect very distant galaxies. In fact, there are already 2 galaxies that we think have been detected that have redshift of 11. And enough. You've been very kind, and I thank you for your attention.
Thank you very much for this exciting results. Questions?
Which is the? I mean, you are speaking about the successes. Which was the biggest disappointment from Hubble for you? I mean, except of the beginning, what it didn't do and was expected to do. So good.
Can you help him out?
Some of the, I can't think of a disappointment, I must say. But some of the successes, of course, were not predicted, unforeseen. You know, acceleration of the universe? No. Black holes, it was thought that maybe it would have success, and it did. In terms of cosmology, it's impossible to think of any disappointment because, of course, the success of the original deep field was no one thought that it should even be done. So anything is a success. So no disappointments there. It was not for the solar system. We have all the probes. So there was no disappointment there because the solar system was not expected to be something that would Hubble would make an important contribution to. So what does that leave? That leaves stars in our galaxies and their analysis, and nearby galaxies, stellar populations, and most of the things I can think of there have been successful. So that's so my credibility is damaged because it sounds like I'm being what we call an apologist for the telescope. But maybe this is one of the reasons it's been considered such a success. Honestly, cannot think of a disappointment. The outreach, I will come back, I say this to everyone, which of course was not anticipated, right? But it would have been a real failure if we had not done it. And I again point to it as a really important success. So I don't like to appear of being an apologist, but that's my honest assessment. But so I'll start thinking. There's got to be something that I can give a better answer to, but I can't think of what it is.
It seems in the numerical simulation of the MRI effect, the jets are now well contaminated.
Yeah, that's right. So it's hard to know whether that's because of the approximations they made. Yeah, I note the same thing, and so I don't know what to say. Other than if we're really going to believe that is the MRI that's doing it, I think one has to demonstrate that you do get the collimation that you observe, and we're not there yet. And so I suppose that means that maybe the MRI is being overhyped. I don't know. There's no alternative that I know of. The MRI, you know, and what's so nice about the MRI is you get the transfer of angular momentum outward, and you get mass transfer inward that it allows to create. So it really is a very clever idea, which is why they got the Shaw Prize, but maybe there's still problems that we need to understand better about magnetorotational instability.
Other questions?
Their data
Hubble collected which have military implication so that they are classified?
The opposite. No. The short answer, no. It's the opposite. Interesting. So one of the really interesting books in astrophysics in the past 20 years was a book called Cosmic Discovery by Martin Harwood, published by MIT Press in 1981. And Martin Harwood was the director for a while of the National Air and Space Museum, right? Most visited museum in the world, turns out. And he, interesting thinker, and he commented there in several chapters of the influence of military research on astrophysics, all right? I mean, our infrared detectors come from the military for obvious reasons. So the answer to your question is no, it goes the other way. There's nothing about Hubble that is classified, has any military implication. And while we're talking about it, since I always like to think that it's always good to have things changing, I happen to be an advocate for some major changes. One of them will not surprise you, in the way peer review is done. Right now, the peer review system in astronomy worldwide is the same. It's community-based. Basically, proposals are submitted, you have 100 astronomers coming once or twice a year, and they evaluate the proposals. I believe that it's an excellent way to base a peer review system on, but it lacks diversity. Hubble Deep Field would never have been accomplished through that. It required director discretionary time because it was so risky. And so one of the things that groups tend to do is minimize risk. One of the things that individuals do, some individuals, is you take risks. And if you believe that creative ideas tend to have their origin in individuals as opposed to groups, which help bring them about, I believe that every unique facility, whether we're talking LHC, astronomy, whatever, should have the director assign at least 25% of the facility, rather than community. That will give you more risk, more interesting results, also more failure. So that's one of them. I also believe that the whole peer review system should be changed in the way positions are handled. Yeah. But go ahead.
So is that part of the reason why Russia and China, etc., are not interested in sending the telescope into the space, like Hubble?
Well, I think they have some interest in doing so. I would be surprised if that were the reason. I'm not sure what you're suggesting. You think that Russia and China are not interested? Why?
I don't know.
Well, I'm not sure if it's true that they're not interested. The Chinese have some interest. The Russian, I'm not sure about.
Where's that program?
Excuse me?
Where's that? X-ray satellites.
Yeah, yeah. But I think they're minor on that, though, right? But I would accept that point.
Okay, other questions? I'm actually curious about the fate of Hubble.
There are engineering studies done by Goddard that show, and they're fairly reliable now, that if you assume after every servicing mission the telescope is working 100%, there's a curve that gives you the probability of a major failure. And it becomes 50% at 4.7 years after the last servicing mission. We are now almost at 4.7 years. So the telescope has been working perfectly. It's amazing. Better than early on with the new instruments, the new central processor. So we're due for a problem. And it can happen any day. So there are different ways in which the telescope can fail. If a micrometeorite hits the mirror, that's it. But we have, or one of the two high gain, well, we've got two high gain antennas. So, you know, in fact, they're already as a whole. It's interesting. So I was just at MIT because just 2 weeks ago we celebrated the 20th anniversary of the famous first servicing mission. Had a big event there, and all the astronauts were there. And they were showing a picture. You can stick your finger through a hole in the high gain antenna, one of them. So Hubble has 5 working instruments. So if one of them fails, you've still got the other 4. You'll lose some capability, so that's okay. So it depends. So we're living on borrowed time. And every weekend, for some reason, the failures seem to occur on the weekend. It's true. It's true. You know, you come in Monday morning, there's a message. So went into safe mode. And so right now, I would say because the great expense of Hubble was the servicing missions, they're really expensive, the launches. And so it's relatively cheap to operate now with just our institute. 50% of which is data reduction funds for the community. So that's, you know. So I believe that Hubble will continue to operate until, as long as it produces useful data, which means either WIF3 or ACS. STIS maybe, but as long as one of them's operating. But the reaction wheels will go, although they're in good shape, new batteries. So with a little luck, we're hoping that the telescope may last until James Webb is launched in 2018. After that, the phase of the, what is it called, Class A requirement is, because Hubble will not burn up, you know, it's too large, it is to be deorbited. We don't have the manned capability, but on the last servicing mission, a little ring was installed back into the telescope. It makes it possible to stick a robotic propulsion unit. And so right now, well, nothing is planned at the moment because Hubble should be able to stay up there through another 1 or perhaps even 2 solar cycles. What limits it, of course, is the solar activity in the 11-year cycle. So it heats up the atmosphere, and the drag right at the maximum is what causes its orbit to decay. But we're in pretty good shape, and so in fact, there's a very good chance it'll last in its current orbit for 10 years, maybe even 20, which means that you don't have to worry about how we're going to bring it down. But the fact is, NASA is committed to deorbiting it, but sadly, it's probably going to have to just be deorbited into the Pacific Ocean. We have no shuttle anymore that could actually bring it back. Many of us think that an icon like that would really be nice in the Air and Space Museum, but you know, I have dreams that Bill Gates will give $1 billion. But without the shuttle, if the shuttle were still there, it could happen. But without the shuttle, we're going to have to develop something completely different, and we don't see that. So I'm afraid, with a little luck, it'll keep operating another 5 years with some of the instruments. But you never know. I mean, space is a risky place.
So I think this is a good point to stop. But if you have more questions, please come forward and ask.
Happy to talk to you. You've been a great audience. Sorry I took too much time, but
Oh, no problem. We all enjoyed it. Thank you very much. So that's